So today I'm going to talk about, I guess, some work that's partly speculative and partly based on the work I've done before, and it's about how we can design AR content keeping in mind human perception and how people perceive how people perceive the world around them. So what does this mean? So the problem I'm looking at is that how can we use some of these new algorithms in machine learning or artificial intelligence, what have you, to design content for augmented reality or virtual reality that can evoke a certain emotional or invoke a certain emotional response. And so I think the challenge that's mainly there, the technical challenge is that how do you actually measure human perception? What do I mean by that? How can you quantify or understand how people perceive visual information, and then how can you use this data to train machine learning algorithms to then modify or augment visual content to invoke a certain visual response, a certain emotional response. So I guess what I mean by quantifying human perception is that given visual data, whether it be what your camera is looking through a AR headset or whether you're looking at a picture taken by camera, what emotional response is generated by this picture. So maybe I show you a picture like this, which is just like a normal suburban street, and that may not be as memorable. It's probably it scores very low on the scale of memorability. So maybe I will give it a 1 out of 10. But if I see a scene like this, maybe that's really memorable. I think you'll probably remember if you see a car with a big lobster strapped on it driving around. So as you can see, there's a dimension to this, which is the emotional response invoked by this picture, and then I think a lot of these pictures will generate emotional response that's pretty consistent across people, and that can be in some ways quantified. Essentially, I started working on this problem a few years ago, where our goal actually was to understand if we can quantify human visual response to street scenes, to outdoor scenes. If I show you a picture from a street, can I actually predict what your emotional response to this picture would be? So, for example, if I show you a picture from Google Street View, would I be able to predict how safe you think this place looks, or how beautiful it looks, or how lively it looks, and so on? Can you actually use a computer to predict this? As any standard machine learning researcher would do, I said, okay, how can I go about solving this problem? Maybe I need to collect some training data. So essentially, what you would do is, if I can collect enough training data on how different people perceive a place, I can then maybe train a machine to predict this quite accurately. And I have my favorite hammer called, say, deep learning, which can take visual data and then assign labels to it or understand the visual content. The first challenge here is that how do I collect training data? How do I get large amounts of data on how people perceive pictures? So in my case, we built a crowdsourced game. Maybe let me tell you a bit more about, I guess since I talked about deep learning in the panel talk, let me tell you a bit more about what the technology is and why it's being widely used in computer vision, because this is sort of the standard workhorse that's now being used to understand and interpret visual content. So essentially, deep learning is neural networks which you can train to do certain tasks on, say, in this case, visual data. So for example, now we can do tasks like recognition. So given a picture, I can identify what objects are in the picture. I can put bounding boxes around them. I can give a label to what objects present. So I can do these kind of recognition tasks. I can also do things like semantic segmentation. So given a picture, I can assign labels to each pixels for what object it belongs to, and I can have very low-level, pixel-level understanding of the picture. And I can also generate text information from pictures. So given a picture, I can generate descriptions, sentences, which pretty accurately describe what the picture contains. So we can do these kind of image to text kind of tasks. And so all of this is powered by neural networks to which you can feed raw pictures and you can feed their labels, and the algorithm learns to then do this particular task. And so just to give you some idea of why these methods have become really popular, we have seen dramatic improvements in accuracy for these tasks by the use of deep learning. So here you are seeing error rates on a popular image classification data set. So it's a standard benchmark on which algorithms can compete. And then since around 2012, when deep learning became popular, now we have algorithms which reach or even beat human accuracy on this data set. So we have sort of a very powerful general purpose tool that can be used to understand visual content. So in our case, we are concerned about the problem of how can you predict human visual perception. And these deep learning algorithms need a lot of training data. So we essentially need to have a set of images and their labels which then can be fed to the algorithm. So in our case, to generate these labels, we built a crowdsourced game. We showed people pictures from Google Street View and asked them different questions like which place looks safer, which place looks more lively, which place looks more beautiful, and so on. And so you could come to the website and maybe you think that the picture to the right looks safer, and you could click on that and we would record your response. So that's the way we essentially built a system to collect your responses. And this method has some nice properties. It's more stable than asking you to rank something from 1 to 5 or so on. And then, but we do need a lot of human responses. So we, being at the Media Lab, we have access to a lot of media and popular media and print media. So we did a bunch of publicity. We published a bunch of articles on why you should come play this game. And a bunch of people read these articles and came to our website and gave us these comparisons. We also did a bunch of Facebook advertising. And in this way, we collected thousands of responses from people across the world. So in this first survey, we actually showed people about 4,000 pictures from 4 American cities, which were drawn randomly from Google Street View, and then we collected more than 200,000 comparisons from about 8,000 people. So essentially, we collected a large number of responses from people across the world. And these sort of were the basis for our labels. So what we could do is we could take these comparisons and then we could convert them to ranked scores. So we call these scores street scores. So we are taking these many comparisons between 2 pictures, and then we are saying which picture has the highest score because it gets selected the most among all these pictures. And so you can essentially convert these to score between 0 and 10. So a picture that gets selected all the time maybe gets a score out of 10 out of 10. So here are some examples of images with low street scores or low, in this case, perceived safety. And you can see these are empty streets and parking lots and so on. And then you can, here are some examples with high street scores. I'm sorry, it's sort of getting chopped. But yeah, so these are pictures which have high perception of safety for thousands of people who are coming and rating images on our website. Then we can train a vision algorithm. So we can train maybe a convolutional neural network. We can take all these pictures and then their labels, which in this case are these scores for perceived safety. And then a neural network can essentially learn the associations between the image pixels and these labels, and it can predict the perceptual response of new images in our data set. So it can pretty accurately predict what human perception would be. So in this case, the relationship here is, so you get a R-square fit of about 50%, which is a measure of telling you how accurate is the fit between real and predicted data. And for an application like this, that's a pretty good performance for an algorithm. So just briefly, we can use this to actually score thousands of pictures. We can go to Google Street View and then we can rank images drawn from Street View, and we can create really detailed maps of human perception across the city. And we actually have an interactive website where you can go and see these responses. So you can click at any place on the map and it will show up the picture and its predicted score. And it also has applications in things like urban planning, because you can look at human perceptual response across years, and then you can understand how places are improving or declining. And that's another application that we have shown for a data set like this. But in the context of AR and VR, I think where data like this is interesting is in actually be able to generate images. So there are these newer methods called generative adversarial networks, which are a type of neural networks that have been proposed recently. And essentially what these methods do is that they can you can feed them real-world images, pictures taken from the real world, and then you can essentially train the algorithm to generate pictures that look very much like the real-world images. So you can train a computer to generate visual data instead of predicting labels from visual data. And these methods have advanced rapidly over the last year or so, and so there are now things like cycle GANs or generative adversarial networks, where you can, instead of generating images from raw data, you can generate images that map to a certain property. So for example, you can do things like style transfer. So given a picture, I can show it examples of different types of artist styles, different types of painting styles, and I can then generate images which have a certain style based on existing data. And so in this case, what you're doing is you're taking a picture and applying it a certain style or certain type of transformation that gives a certain property. So where I'm looking to extend my work is you can use similar techniques to then transform images along the perceptual dimension. So I can make an image maybe more scary, more beautiful, less scary, depending on the dimension you're interested in. You can modify the visual content to invoke a certain perceptual response. And that could be useful in augmented reality, either by adding objects to the scene that will invoke a certain response, or in virtual reality, where you could create scenes from scratch that can generate response. So you can do things like image editing. So if I know how people perceive different things, maybe I can add objects like trash here, or I can add, for example, these electric wires, and that would change your response to the scene. And you can learn these kind of data. You can learn these kind of associations between objects in the scene and perceptual response by using the training set that I've generated. Great. So in short, I think the idea here is that typically we have used machine learning to understand visual content, but we can also use machine learning to understand and predict human perceptual response to visual content. And then this, I think, can be used in turn in AR content design or in virtual reality content design by adding or subtracting visual content, which will change your perceptual response to the visual content. Thanks.